Thank you, Tristan, and everyone. Hello, welcome to CloudFest AlmaLinux Day. I'm really happy to be here. We're gonna take a level above operating system. We're gonna talk about databases. My name is Roberto Luna Rojas. I am a developer advocate at open source in AWS. And today we're gonna be talking about two hard things, cache invalidation and naming things. And I'm gonna talk to you about a specific project that got the naming right from day one, Valkey. You raise your hand if you have heard about it? Yeah, probably a couple times today. And it's an anagram of key val that comes from key value. Essentially, it's a key value in memory data store. And the main thing that it does is cache. We heard a little bit about today from what Jonathan is doing for the mirror system for AlmaLinux that caches. We also heard from folks on the telescopes as well from AZO. And this is a very famous quote from Phil Carton that it's probably about the mid 90s. There's no actual reference to the very first time that it was said. But I will add another thing. It's usually called there are two hard things in computer science: cache invalidation, naming things, and all-for-one errors. But what is caching? Essentially is a system or a way for you to fetch data that is frequently accessed, and that's why we just heard from AMD how they have that in processors by providing, I see there were some up to 32 megabytes of L1 cache, and we see that all the way to what Jonathan talked about earlier when the mirror system. So it goes from the microchips all the way to DNS and CDNs, right? So essentially what Jonathan has in the mirror system for Alma, it's essentially a DYI CDN. But the main thing is you try to avoid going to the source of truth, so you put your data on a faster system, so that could be multiple tiers. We heard earlier today as well about CERN, right? How they have that ultra fast, a lot of data that need to be storing, so that goes probably to memory, then disk, and then at the end to tape. So whenever you're reading it backwards, then you do that as well, right? You put it on a cold, and then if you need to fetch it, you put it in a warm storage, and finally, memory is the hot storage as well. I'm going to tell you a little bit about how Valkey came to be. It's a key value memory data store. It's a project that's usually mainly used for caching, session store, leaderboards, message queues, and even can be used as a primary database. It is a fork of Redis 7.2.4, and it's a project under the Linux Foundation, making it vendor neutral. And it's built by the contributors that used to create Redis as well. So very similar to Alma, right? Alma actually also got the name pretty right from the get-go, which means soul, right? It's the Linux of the soul or something on those long lines. In the case of Valkey, you usually come for the software, but you stay for the community. All the people around it and that like to contribute got together back in, I think it got, there you go. Bear with me on this slide. I have a lot of links that I'm going to be referencing to you, and hopefully you can go and dive deeper later. But I was saying, back in March 20th of 2024, about 2 years ago, the Redis company decided to change the license, right? They were owners of the project, so they could. And within 8 days, the community got together, created Valkey under the Linux Foundation, and it was announced on the 28th. By April 16, we had already a release candidate for Valkey 7.2.5. And actually, a few days later, Jonathan was one of the first packagers and one of those unsung heroes, right? Like, it doesn't matter how good software is if no one can use it, especially in open source. So putting it out there on a Linux distribution, in this case, Fedora was the very first one that took Valkey as a Redis replacement. And a few months later, he actually was staffing the booth as well as Open Source Summit in Europe when we released the very first GA version of Valkey 8.0 that came in with a lot of things that we have learned at AWS to provide better throughput, right? So essentially, one of the main issues with the original version is that it was single-threaded. It doesn't matter how many cores the chips have. Like if you only have a single core that you can run your operating system and then the bulky, then you're not taking a lot of advantage. So what we did is open source something that we've done at AWS, which is taking advantage of the other cores with IO threads. So that means that a lot of the parsing of the commands and doing all of the IO operations, it's pretty heavy. It's about 70% of the time. So then you take a command, whether it's a write or read, go fetch it from RAM, and that's actually extremely fast within a couple microseconds. And then you assemble the response back and send it back to the client, right? So with that, we went from 380,000 requests per second to 1.2 million requests per second. So that's a significant improvement that in that case you can reduce the amount of servers that you have if you have a throughput bound workload. Later on, AlmaLinux as well. I'm sorry, that's back when we announced it, then AlmaLinux was there at the OSS EU. And then in March 31st of last year, we announced Valkey 8.1, and we also added a few more features such as JSON support, LDAP, and vector similarity search. Those as separate modules, but we also did something very important, which is memory reduction. From the original version of Valkey 7.2 to 8.1, we were able to reduce about 47% for small payloads, which is actually something that is very commonly used for whenever you're doing counters or just very small key values, especially with nowadays that DRAM is very expensive and most likely the CERN is buying everything. But I don't know, the clouds. And finally, last year in October, we released Valkey 9.0 that increases significantly how fast and how stable you scale clusters. And we're going to dive deeper a little bit on how that works behind the scenes. This is a quote that I got from Jonathan that's about the mirror system. And this is extremely important, right? When do you need a cache or why do you need it? To reduce time, latency, it's one major dimension, but the other one is cost. I've seen, especially now with Gen AI, doing inference could become really, really expensive. So some of those companies that are doing this at scale by introducing a cache, whether it's prompt caching or semantic caching, can save up to 92% on inference cost. So thank you, Jonathan. I'm going to quote you on this from now on. And but how do you do it, right? Like today, I want you to walk out with 3 different ideas in mind. That you have to have a taxonomy on how you name things. How do you decide? And some performance numbers that I already talked about a little bit. So one of the issues of naive caching is that there's a study from Twitter of the Pelican team that they say that between 30 to 60% of the data that is cached is not read a second time. And that, in terms of, for example, CDNs, could be very costly, right? You have those one-hit wonders. The idea is not to do that, but at the same time, you do need to identify when you have data that is required. In the case of something like the mirror system, you probably have like core packages that need to be on RAM at all times. And the ones that are not, it's fine, right? If it's a niche package. And something also extremely important is how to manage the poorly named keys and thundering hertz. And we're going to dive deeper a little bit on that. So this is probably a misconception. We usually think that, yeah, this is a happy path. This is the diagram that we see on books, textbooks, very simple. You have a cache. And then if you hit it, fine. That's response super fast. If not, you go to the source of truth, in this case, a database, and that will be, let's say, a database, an average 50 millisecond response. The reality is that you get this, right? So Do we have different teams working on similar parts of architecture on the system, and you end up with a mess that looks like this, where you have multiple keys for the exact same data. In this case, you have user colon 42, and that could be stale, and then you have a capital user colon 42 that's just duplicated and it's wasted memory, especially nowadays that is so expensive. And then you have legacy formats, and you probably have even some misspelled keywords as well. In this case, USR, right? So that probably never actually accessed nor invalidated. So that means that you're probably just hitting the backend data store over and over. So how do you avoid these 5 caching mistakes, right? So one is the key naming contract. You have to um, try to reduce duplication of storage and avoid collisions. So this is a very common one, or the top one. TTL as your only strategy, or even worse, not having a time to live. So that means data just stays in memory, is not invalidated, or if you do, and it doesn't have a proper longevity, then that means you're gonna get stale reads, thus pretty much useless data. Or if it's too short, you get that thundering hurt as well. The third is having cache aside everywhere. That is the most common, the most simple pattern to use, but that doesn't mean you're gonna be successful, especially when there's multiple writes happening. There you go. No observability. That means not looking at your RAM or your metrics on how many keys and how much RAM you're using. So essentially, you get a lot of bloat that sadly happens until it breaks, right? So you get a lot of max memory utilization, you start getting fragmentation, and you see side effects of things that should not be happening because poorly managed observability. Other thing is if you have, like in this case, Valkey, data types that are collections that could be extremely large. By default, it used to be about 4 billion items on a single collection. Now it's 2 to the 48th. So it's a lot more than that. So you have to be careful about what you're feeding into RAM. And no invalidation path or graph. That means that one key, in this case, if you have a product, and that product needs to be updated, whether it's the price, the description, or something else, then you have to go and invalidate all of the other keys that have the data for that product. Let's say you have a hat, right? So that hat changes prices, and maybe that's a trending product, so that you need to go and invalidate that. You need to go and invalidate all of the other keys where that hat is also being shown to different users, right? So maybe you have like men's wardrobe or whatever on a shopping cart, then you need to go and validate that as well. So naming and invalidation are not separate problems. They're one big problem that we can go and solve. The very first thing that I have for you is a taxonomy, right? So you need to provide some sense for this. There's a common grammar that you can use where you have a namespace, the entity, the identifier, and qualifier. And yeah, no, it's a little bit short, yeah, but essentially you have different examples here that are bad and good. Some of the good ones is when you address this by using the common delimiter that everybody knows and adheres to. Colon is the most common one in most caching systems that goes to memcache or even local cache as well, or in the case of Valkey as well. And you have something like the SQ or a UID. And bad keys is similar to what we talked earlier, right? When you have case sensitivity, you have something even worse as just random keys like temp. And in this case, the very, very common one is having an environment. I think I have a slide next to this. Going, there you go. Environment, yeah. So one of the very, very common is having environments that's not ideal because essentially you have duplicate keys that are named differently, and you don't know how many keys you have per environment without having to rescan the whole thing. The other is you have to take care of something called cluster hashtags, so the curly braces specifically for Valkey, and we're going to see how that affects in a second. And by having a namespace divided by a common character, you can also do scans without having to, with using the glob pattern, without having to scan all the millions of keys or even billions of keys that you may have in a cluster. And try to keep them short. I talked about memory reduction that we've done on Valkey 8.1 and onwards, but that only applies if you have short keys with short values, right? Like if you're gonna use, I've seen keys that are like 1K or even worse. That's not ideal, right? So you have to be frugal in usage of RAM. And similar to how you version APIs, it's also best practice to version your keys as well. So going back to what a cluster is, you can run a Valkey cluster that is a single node, right? That's perfectly fine. That's a standalone node, but that's not going to be very production-like. Some way to distribute the data on a sharded system is by splitting it up into multiple. In this case, I have 3 different shards split in different nodes. Each one of them is going to be responsible for a subset of the keys. And the way that the data gets routed is you have a key, in this case, user colon 123, and then what's going to happen is there's going to be a CRC16 hash divided by the total amount of cluster slots, in this case, modulo 16,384, and that's going to yield a slot, in this case, 12,893. So that means that the client already knows which set of nodes is responsible for that key. And that's how you get extremely low latency, regardless of how many nodes you can have. On Valkey 9.0, we are able to have up to 2,000 nodes in a single cluster and up to 1 billion requests per second. So probably Alex and the CERN can start saving that data that they capture if they have a bunch of Valkey clusters. Okay, having said that, now that you have the ability to distribute the data, that's what you should do. But in this case, whenever you're naming the keys, the way to trick how to have similar or group data is by using curly braces. And that part of the key is the one that is going to be hashed. In this case, if we have products and we have an SQ that is 82917, all of the relevant keys for that product will remain on the same shard. So whenever you are touching, for example, the price as well as the details, you can go and do that atomically in a single round trip to that one node. If you do use something like curly braces on the entity, in this case the product, you're going to have a lot of trouble by causing a hot chart, right? Most likely the catalog is going to be, or at least the top products on the catalog are going to be the most requested keys. I have seen this in streaming services that they were really hurting when they had an issue like this, where they had, for example, an ad, right? Like pizza or whatever. So that means they were getting 40 million requests per second to that one shard. So they needed to keep adding more and more replicas to get that key. So the way to solve that is spread around, right? Don't do this. And the way that you can actually solve this is by having multiple copies of the same key distributed evenly across the cluster. And you can do that deterministically by having a prefix or a suffix of the key name, and then you say, okay, I have this queue of the ad or the product, and then you say, I'm going to add value from 0 to 9 or from 0 to F. So you have 16 copies of the data, or even if you need more, right? You can have 2 hex values, and then you get 256 copies of the data. And that way you can distribute and get billions of ops per second. This is something that you can share with your teams and start using on Monday, right? It's a very simple Python class that just takes a key name and then you have the different pieces, so you have a deterministic way of creating keys. But look at this, there's if you get a list of strings, actually it's best seen on the next one, you're gonna have a better response whenever you're starting something like this. When you're doing a comparison, in this case, SQ100 versus SQ42, you need to be deterministic on how you go about it, because the permutations, if you don't have them ordered, every combination, every way that you send the keys is going to create a brand new key, right? So we said we need to be deterministic. In this case, they're sorted, so it's always going to yield the same SQ100 colon whatever, right? So we're going to order them by their ASCII alphanumeric values, right? So an pattern, like I said earlier, um, environment in the keys is not great. Serializing keys as well. This is so very, very important. It goes back to the what I was just saying earlier, right? Like sometimes people just get the whole string of whatever they're storing. This could be a SQL query, but it could very well be a graph or an analytical query as well. If you're using Mongo or ClickHouse or anything, OpenSearch, they all have the same problem. The permutations of what this is going to yield, right? In this case, I have a predicate here that it says where A equals to 1 and B equals to 2 is different from where B equals to 2 and A equals to 1. Because at the end of the day, we're just key value, right? Like for us, it doesn't matter the order of the factors. It's like, well, if it's different, it's different. So you have to be deterministic whenever you're tokenizing. So the approach is to be and just hash the value canonically to always yield the same response. Timestamps, that's not sortable, right? That's also not invaluable. So you have to put a TTL on its own, but it's going to be super hard to find. And yeah, I have another example. When using large keys, I talk about how streaming services usually struggle with having, or in this case, retail as well. They can store whatever, right? Up to 512 megabytes of data. But in this case, if you have JSON, XML, or anything, uh, it may not be a good idea to have to serialize the object, send it through the wire, store it, and then whenever you need to update a little piece of it, then you need to go and get it, deserialize it, make an update, serialize it, and then go and start it again. Best approach is to use a dictionary. In this case, Valkey already provides something called hashes that you can have a top tier level of elements, and we also have support for JSON. So the idea here is that if you only need to go and update one item, it's gonna solve for bandwidth, right? So speed, because you're not gonna be storing the whole thing and doing the serialization and everything. The amount of bytes that you're gonna send through the wire, and more importantly, you're gonna solve a problem of race conditions. Let's say somebody needs to update the price or the inventory. Let's say we have, I forgot what stores are here, but Walmart, which is not in here, you're gonna go and update the inventory of a product, right? So there's gonna be multiple different clients buying for that, and then you will need to go and deduct or increase whenever there's more inventory. So that's gonna cause like last right wins. So very, very simple solution is just go and use hashes. So there are 4 different strategies that you can take advantage of for doing cache invalidation. I said that cache aside is not the only one, or TTL shouldn't be the one as well, but it's of course the most simple. The way that you will think about it is for how long you want to keep data on. So if you have very simple use case, right, so that you can just have hours, let's say everything on a 24-hour cycle, then you're very well storing just the TTL and let it invalidate by itself. If you have an event-driven system that data changes within minutes, then you need to apply some change data capture using something like Divisium. And then if you do have something that changes very, very, very frequently, like stock prices, happens within seconds, then you need to take a write-through approach, or worst case scenario, a write behind. I talked a little bit about Thundering Herd, but let me explain what that is. I think this just keeps. How can I move? Thank you. The Thundering Herd problem, right? What happens is that you get a lot of clients going fetching data at once. And one of the issues with the TTL approach only is that you're gonna go and cost that. Like if all you rely on is the TTL itself, we go forward. Okay. Or a way to solve it, right, is by adding jitter. And we're going to see a graph on how this plays out. But the idea is that you can append or remove some of the time. So, for example, if you want to cache things for 60 minutes, you randomly select like, oh, I want to cache for plus minus 10 more minutes, right? So things are going to be validated within 50 or within 70 minutes. So that's a way to even out the load. A better approach, or something that you can add on top of that, is xfetch, where you play with um, doing faster invalidations every time that you fetch the data by introducing a delta. So that means that for more, a beta, that you want to try to keep to 1.0, right? That by default is going to be, the closer it gets to the TTL, is going to expire. But if you have more slow system, like an analytical, let's say you have a dashboard, and then that a query takes 2 minutes to run, then in that case, you're probably going to go and fetch that proactively faster. If you're okay with something like I said, the stock price, then in that case, you probably want one of the clients to go and proactively prefetch that, but it doesn't need to be as bad, right? If it's coming from a fast system like another NoSQL database. We move forward. Yeah, so that's the graph that I was talking about. Whenever you do rely only on the no jitter, that means you set the TTL, you're gonna get something like the red line. But if you do even it out by adding the jitter, then you're gonna have a smoother bell curve, right? So that means that you're gonna even out the amount of requests going to the source of truth. In this case, if it's a backend database, you're gonna have a lot less trouble on the backend system. All right. The event-driven approach is, like I said, something using like Division, which you take changes that happen on the backend database. This could be something like Postgres or MariaDB, whatever of the systems that it provides. So you can just go and delete proactively that key, and then you add cache aside on top of that, right? So the next customer or request that requires the data is going to go and fetch it. But this is just a simple way to try to have no stale data on your system. And this is pretty much what you will have to do, right? So you have to add a little bit of complexity on the write path. So whenever the update happens, you need to provide some metadata that gets pushed to the system. So that means that there's a worker listening for those changes, and then you go and invalidate, in this case, the catalog. Okay, and I talked about two others, right? Write through, which means it's synchronous. So the application will essentially have to write to both the backend database as well as the cache. That way you will have always fresh data. And this is, like I said, extremely important for something like financial systems where you need to have like the last value of stock, or in this case, something like your application for the bank. Like every time that you make a purchase, it needs to go and update both the credit and the debit. And right behind, it's a lot faster, but the problem is it's asynchronous. So if one of the systems doesn't take the changes, in this case could be the database or the cache, it could be problematic. And using that key creator, it's fairly straightforward to use that. The only thing that in this case, the fourth strategy is adding tags, right? So I talked about the graph of dependencies. Whenever you need to go and say, okay, I want to clean up or update the product, so I also need to go and find the categories that it belongs to, or all the promos, or everywhere else. So you need to have a collection of keys that have the same amount of, or the same keys that are relevant. And if we go next, yeah, these are just some extra slides that I have if I needed more time. This is important. The time, as we can see, the top Valkey responses are a couple hundred microseconds on average, and even at P99, we're talking about half a millisecond response time. And whenever we're doing it with a database on a cache miss, it's barely unnoticeable, right? Whereas if we do not have a cache, which is the middle and the bottom, using whether MariaDB or Postgres, you're going to have very, very high P99 or even P90 or 95 latencies. Okay. This is just some extra numbers. You get about 37% better, 35% better optimization when using a better strategy than just a naive cache. And the idea is to take you, if we can go to the next, yeah, from that red line where you are doing a lot of throughput to the backend database to be on a stable green line like below by taking advantage of these strategies that I talked about. And we go next. This is the decision matrix. The idea is that you can take this and have it on your team whenever you need it. And yeah, I think we're good. We learned today about the taxonomy that you have to take care, the strategy that you have to identify in order for your data, and for how long you want to try to have your data on the cache, observe your metrics and performance. And finally, these are a bunch of links that I have, as well as code examples on how to run your own test on the next slide. And yeah, finally, you can find me on LinkedIn, X, the next slide. Thank you so much for the time, and I hope you learned something today.
We have a few use cases at work where we deal with data, where we have a smallish percentage of data that is hot, basically. But a lot of data is not that hot. So when it's difficult to determine a good cache strategy on the application level to separate them into, for example, a memory-only cache and a disk-backed cache. And what we have been using is KV-ROCs, for example, as a strategy to address this. But I always wondered if it would be not easy, possible to add simple maybe solutions on top of Redis or now Valkey to accommodate these kinds of use cases better, like where you have some kind of transparent, persistent, maybe optional backing cache. Is there something planned like this for Valkey? What do you think about this?
We're working on it. There is a issue where we discuss having a tiered storage. So in this case, we introduced a module that can store data on Postgres automatically, and even S3 as well, right? So I was talking about the different tiers where you have hot, warm, and cold. So we're trying to work on that. So if you have any good use cases, that would be great. The way to identify which is hot and which is not, you need to figure out your cache hit ratio. And then the subset of keys, we do have some observability metrics on Valkey that we've introduced to see which keys are the ones that you really need in RAM.
Okay, so you're working on it.
Yeah, probably 10. But we're working on it, yeah.
Okay.
Thank you. Anyone else? Yeah, I'm going to let the next speaker go.
Thanks, Robert.